Hello everyone, I'm SJBIT, working as Assistant Professor in the Department of PC SJBIT. In this lecture, we'll be discussing about computer organization and architecture.
So this is about the instruction. Here you are able to see that this is an example of the. So this is about the instruction example. So there are example. So add a plus b multiplied with c plus d. So three addresses. One is the add r1 comma a comma b is nothing but the memory address of a added with the memory address content of b, and that is getting loaded with r1. Next, add c, the memory content of c plus the memory content of d is getting added and loaded with the register r2. So next it is multiply. So the register content of R1 and register content of R2 is getting multiplied and moved to the memory location X. So next it is the three addresses instruction, that is add R1 comma R2 comma R3, that is the R1 and the R2, the register content is getting added and given to the register R1. Two address instruction, is nothing but add R1 comma R2, that is R1 plus R2 is getting added and move the address to the R1. So one address instruction, that is add m. Add m is nothing but one address instruction, that is the memory content of auxiliary carry, that is AC is getting added with the memory content of AR, and result is getting saved with as AC. So what is instruction it is going to have? Instruction is going to have opcode, operands or address, and this is going to be the opcode of the instruction and this is the operand of the instruction. So zero address instruction, only add, it is considered as a zero address instruction. So that is considered as the TOS, or the TOS minus one location is getting add, and that is being stored with the TOS. So in the two address, that is a single two address instruction cannot be used to solve our the problem. So without destroying the either, the sum is going to be stored in the AC. So move B comma C. So here. So next is the RISC instructions. So a lot of registers and the memory is restricted to load and store. So for that we are going to use for the reduced instruction set computing. So where the instructions is reduced, so memory is restricted to load and store. So next is the instruction operators. That is to evaluate a plus d into c plus d can be done in the two addresses. That is the memory location of A is getting added with the content of the R1 and getting saved with the R1 register. So add R1 comma B. So the content of memory B is getting added with the R1 and move R2 comma C. So the content of C is getting shifted to the register R2. So add R2 comma D. So here that is the content of the D is getting added to the R2 and getting saved in the register R2, and now with the multiplication of R1 and the R2. So this is the instruction set only considering the two addresses. So we are not using the three addresses here in this case. So the example for one addresses is the same example, load A. So next one is add with B. Next one is store in T, and the load C, load add with D and multiplied with T and store it as X. So this is going to be a one addressing scheme. So next is the example to evaluate the zero addresses. Push A, push B, and then add, then push C, then push D, add, then multiply and pop X. So this is using the stack and subroutine. So next is to using the concept of reduced instruction set computing. So load R1 comma R1 comma A. So next one is load R2 comma B. The B content will copy to the load resistance. Load all memory locations we are using here. C to the R3. So load R4 comma D and then add R1 comma R2 comma R2. R1 plus R2 plus R3 and the result is getting saved in R1. Similarly, R3 and R4 is getting added and the content is going to be saved in R3 and multiplied R1 and R3 and the result is getting saved in R1. So and store R1 to X. So this is what we are using. So this is known as the reduced instruction set computing. So using registers, registers are faster. So which is store the instructions and the number of register are smaller. For example, 32 register needs 5 bits. So the potential is going to be speed up if you use the more number of register. It is inbuilt with the processor. So minimize the frequency with the data is moved back or forth between the memory and the processor registers. So this is what the instruction execution and the straight line squeezing. So here the assumption is that one memory operand per instruction 32-bit word length, memory is byte addressable and full memory address can be directly specified in a single word instruction. So that is begin execution here. The content of move a comma r naught. So I plus 4 that is add r comma b naught and move, that is each time it is incremented by 3 instruction program segment. So data for the program, that is 32-bit word length, memory is the byte addressable, full memory address can be directly specified in the single word instruction. Two-phase procedure, instruction fetch and the instruction execute. So branching is nothing but the straight line. It is the branching is nothing but the offset is getting added here, and that is going to move to the. It is going to branch the instruction to the next uh, memory address. So which is considered as the So here in this example, you are able to see that the address of the memory location containing the n numbers are symbolically represented as the number 1, number 2 and number n, and the separate address instructions are used for each number of contents of the register R0. So after all numbers have been added and the result is placed in the memory location considered as a sum. Instead of using the long list add instruction, it is possible to place a single add instruction from the program loop. So the loop is straight line sequence instruction executed as many as needed. It starts the location of a loop and ends the instruction when branch is greater than 0. So during the each pass of this loop, the address of the next list entry is determined and that entry is fetched and added to order. So the address of an operand can be specified in various ways. So assume that the number of entries in the list of n is stored in the memory location. So the register R1 is used as a counter to determine the number of times the loop is executed. So the content of location n are loaded into the register R1 at the beginning of the program. Then within the body of the loop, the instruction decrement R1. So this reduces the content of R1 by 1 each time through the loop. So the execution of loop is repeated as long as the result of the decrement operation is greater than 0. So the branch instruction, this type of instruction loads the new values into the program. As a result the processor fetches and executes the instruction at its new address. It is called the branch target. Instead of instruction at the location follows the branch instruction in the sequential address order. A conditional branch instruction causes the branch only if specified condition is satisfied. If the condition is not satisfied, the program counter is incremented in the normal way and the next instruction in the sequential address order is fetched and executed. If branch is greater than 0, it is going to be execute the loop instructions. Is a conditional branch instruction that causes the branch location loop if the result is immediately preceding the instructions. So which is decremented the value of R1 is greater than 0. This means that the loop is repeated as long as the all entries at the list are yet to be added to R0. At the end of the pass, loop, the decrement instruction produces the value to 0 and hence the branching does not occur. Instead of move instruction is fetched and executed, it moves the final result on to the memory location of sum. So the capability to test the conditions and sequence sequentially subsequently choose the one of the set alternative way to continue the computation has many more applications than just loop control. Such capability is found in the instruction set of all computers and in the fundamental programming in most of the non-trivial tasks. Thank you.